Good afternoon to the people in the North American region, and maybe good evening to the ones in Europe and in Asia. So, welcome again to IEEE Young Professional Seminar season. So, we have Professor Gunnez. She's from Polytechnique Montreal. She's our kind guest for today, and she will be talking about secure and reliable communication for satellites, mega-constellations. So this is one of the interesting topics that we find, and it's happening recently. Welcome.
Thanks a lot, Timer, for the kind invitation. I am looking forward to discuss some of my findings and an overview of my understanding about the security issues that may pop up in satellite constellations.
Thank you very much. So I would leave the floor to you. Please go ahead and share your brief bio, and we are looking forward to listen to you. The floor is yours.
Perfect. Welcome, everybody. Good afternoon, good evening, or good morning, wherever you are. My name is Güneş Karabulutkurt. I am an associate professor at Polytechnique Montreal, and I am an adjunct research professor at Carleton University. With the Polytechnique Montreal since last March, and before that I was with Istanbul Technical University for about 10 years. My research area is on wireless communications, and today I will talk about the impact of the wireless channel, specifically towards the security and reliability issues for satellite mega-constellations. And again, I would like to thank Timer for this kind invitation, and I'm looking forward to receiving your comments and suggestions after the talk, and you can see my email address on the on the screen. So in this talk, I will first talk about the space networks, actually space information networks. That is a concept evolving towards the 6th generation networks. Then I will talk about the basics of components of physical layer security, which is actually physical security in terms of wireless network nodes. I will introduce the properties of wireless cyber physical systems, and one of the main objectives of this talk is to highlight the fact that satellites are actually a sort of cyber physical system that we can change the location and the behavior. I will later follow this aspect with the security issues in cyber physical systems, which is different than the security in wireless systems, because there are more implications allocated within the mobility and the localization aspects. I will briefly describe the tools and give an example of a case study, and I will introduce a security framework and summarize the open issues and the future outlook perspectives. Finally, I will conclude my talk. Now, I'll start with the space networks towards the 6th generation. As we all know, every 10 years we see another generation in terrestrial networks. It started with the 2nd generation in 1990s, the 3rd generation in 2000, 4th generation in around 2010. Now, around 2020, we are looking at the 5th generation networks. Of course, with this kind of linear interpolation, we are expecting to see the 6th generation networks in about 10 years, in 2030s. Now, the research on the 6th generation networks has already started, and there has been a lot of issues that on which research community has reached a consensus. These include some features, including the use of terahertz, sub-terahertz communications, and the applicability of the drone-based communications, some applications from optical wireless communications. And then there is these meta surfaces and reflective intelligence surfaces. So the technologies are pretty much well thought after, and the idea is to address the ever-increasing user requirements of very high reliabilities, very high data rates, extremely low latencies, and the need to provide support for mobility. And of course, as the number of users increase and the number and the variety of applications increase, we keep we have to design more sophisticated networks. Now, on some of the issues that are included in 6G consensus include the constellations. For this, I will try to come back to today and describe our current network. In the current network, we have a terrestrial network, and we have well-defined UAV-based stations and UAV relays that can work as in a complementary manner to the terrestrial network. This is a well-standardized topic by 3GPP in terms of the fifth generation networks, new radio technology. And we have a good deal of interaction between this air network and the terrestrial network. In addition to that, we are starting to see a standalone space network, which is composed of LEO satellites. And these space networks are envisioned to evolve towards mega-constellations of tens or thousands of satellites. There are some examples that are already operational, like SpaceX, Starlink of SpaceX, and Lightspeed of Telesat. However, we don't have a seamless interaction between the satellite layer and the terrestrial network. Towards the sixth generation networks, this satellite layer will play a more important role, and we will see a more interactive use of satellites with the terrestrial networks. And another new component that is also currently under investigation by the standardization organizations is the high altitude platform station, which can serve as a relay between the satellite network and the air network, specifically the UAVs, and also serve the congested urban areas. So the satellite mega-constellations will be will make more use of it with a full integration towards their terrestrial network, with their full integration with the terrestrial networks. Of course, this kind of network will become more sophisticated in terms of the network management issues, resource allocation issues, and also security aspects. For that, we envision, or the whole research community, there is a consensus on this topic surely, the use of artificial intelligence will surely be more important in this kind of dynamic, sophisticated network management problems. So this is the transition from the fifth generation networks towards sixth generation networks. When we look at this picture in a closer perspective, the importance of the LEO satellites towards global connectivity will become more apparent. These satellites are actually traveling at very high speeds, crossing the North America, the continental North America, in about 7 to 8 minutes. They can also be an excellent enabler to serve the underserved areas. So for global access equality, This satellite networks seem like a very promising solution, not only providing services to urban areas, but also to terrains that are not suitable for ground station placement. Of course, there may be another layer that will be complementary to the issues of these satellite networks, which include the mobility problems and the mobility management problems and the resource allocation issues. High altitude platform station layer may serve as this enabling layer that can help the LEO network communicate with the ground network. Now, another kind of extension that we need to talk about is the use of these satellites and other networking elements, non-terrestrial networking elements like high-altitude platform stations and UAV-mounted drones. Their use will not only be towards the terrestrial communications, but also we are looking at space exploration activities and the two-way connections of the satellites, not only looking towards the Earth, but also looking towards the space, and hopefully looking towards the deep space through in distantly placed nodes, will play a very important role towards towards our humanity's plans towards the extension towards the space, including Mars and Moon and the perhaps other planets. So what is happening is the satellites should be useful for terrestrial networks, but of course they may serve for more purposes than that. The recent plans of the Artemis project of NASA that is targeting the human to send human crews to the moon, for example, is a good case study towards this idea. We will need to extend our communication towards these interplanetary with these interplanetary communication networks. So satellites will serve multiple purposes, and including the possibly space tourism that is coming up. However, they will be their effective use will introduce some additional security aspects. So these are the things that I would like to focus on today in my talk, which is basically the extent of their cyber-physical capabilities, or the interaction of their cyber-physical capabilities with their communication capabilities. Now, the sixth generation networks, and of course with the coming satellite mega-constellations, we will include cyber-physical, aerial, and space networking components. That means these devices will be able to change their positions in space. Of course, when we are talking about satellites, we are talking about fixed orbits, but keep in mind that all satellites have propellers. Almost all satellites have propellers, and then small shifts in their orbits is possible through some commands that can be transmitted from the Earth. Now, with these kind of mobility flexibility, their security will be more challenging. And it's not only relying on the communication information, but also location information. And of course, as we know, and I will try to focus on this aspect today, both the jamming and spoofing problems that are frequently observed in either communication and localization systems can be jointly problematic for these networks. So this means that there will be new threats, and all these new threats must be understood, and effective countermeasures must be developed. And today I will try to focus on some of the countermeasures that can be implemented by the use of physical layer. So what kind of new threats are we talking about? This is a picture from one of our conference papers from last year. And in this work, what we try to look at is the telemetry and telecommand systems, specialized structure. Now, the ground station and satellite has a, of course, command and telemetry interface, and in the presence of an attack to the command towards some command that is going towards the satellite, if we cannot detect the presence of an attack, especially if the attack is meaningful and it implies a spoofing, for example, like a command to change the orbit of the satellite, which may be dangerous in the ever congested space environment, can cause dramatic problems. So these threats have to be well understood and well and effective countermeasures need to be developed to be able to use these satellite networks in a safe and secure manner. And of course, I'll come back to this picture towards the end of my talk again, but just to give you an idea, we will have more capabilities in terms of the networking architectures with communication, computation, caching, and control data. And almost all places we have wireless communication links, and the wireless communication link implies the presence of an attacker in the system without being authorized. The only thing that we have, the most important thing that we have to do, is to be able to detect the presence of the jammer, and this can be more critical than just the mere presence of an eavesdropper, a passive attacker, but also the content of the data can be changed. So this is extremely important. Now, I will first of all, I'll try to emphasize the components of the physical security aspect. What is security? Security is a multifaceted concept. Frequently, they are defined. The solution for security is defined per the Open System Interconnect (OSI) reference layer that it is used in. And the communication systems, the OSI layers, represent different functionalities, and we know that we have 7 layers. And as you can see, there is no security in one of these layers. And this security aspect is usually addressed depending on the layer. Layer 2 encryption, network security in layer 3, application layer encryption, and those kinds of solutions can be are frequently utilized. When we look at the definition of security, it has a number of requirements, main requirements. The first one is the secrecy, where the state that the information is obtainable solely by the legitimate receivers. Not the illegitimate receivers shouldn't be able to capture what is inside the data, what the data is. The second requirement is the authentication, and authentication implies identification of the user and verification that that user is allowed access to some restricted service. The third one is the data integrity awareness, where the trustworthiness of information over its entire life cycle must be ensured. And the fourth one is the robustness. Especially looking at the wireless communication channel, we have the fading and other effects. This implies that there shouldn't be any jamming or natural performance degrading effects, such as unintentional interference causing from other wireless transmitters. Oops. Okay, now what are the attacks that we can see? There are different kinds of attacks. These attacks can be active attacks or passive attacks. In the passive attacks, they are more difficult to detect, and physical layer security issues solutions are mostly addressed towards these passive attacks, which can be eavesdropping or traffic analysis. And there are the active attacks, which includes information disclosure, tampering, man in the middle, or denial of service or distributed denial of service, which translates to jamming and distributed jamming attacks. So there are all these kinds of different attacks. The passive attacks are especially critical because they cannot be detected with current security tools, and we can only use encryption towards these attacks. And they are, of course, they are critical, and eavesdropping attacks imply capturing the data packets by illegitimate users, and traffic analysis attacks imply a type of eavesdropping, but without looking inside the packet. The detection, the presence of a user can reveal a lot to the attacker. So that is basically the traffic analysis attack, trying to predict the state of the user or detect the state of the user. When we look at the problem from the passive attacks perspective, we can implement intrusion detection systems and encryption techniques, but they are usually computationally very expensive. And in terms of the mobile compute, limited power and limited battery life, they become even more expensive. So that is one of the main advantages of physical layer security that is very frequently addressed. But there is more to the physical layer view than the eavesdropping attacks. So, for example, if we look at active attacks in the physical layer, there can be jamming attacks and there can be spoofing attacks. Now, this jamming and spoofing, of course, they have been around for a long time, and it is well studied. But one of the problems is the attackers can the capabilities of the attackers increase. So what I'm trying to say is we have a very simple frame structure on the schema. We have, for example, a beacon, a header, and a payload. And there are some symbols. And for example, we have some pilots within these payloads, and even the beacon and the header, the known signals. Now, the attacker can only do attack at some points of this payload by coupling its transmission with the legitimate user, and the amount of attacks that we can see can increase dramatically. And another issue about this problem is the fact that if the attacker is not using a specific kind of attack, most of the current tools in the literature fail to be able to detect them because their presence is varying in time. Their attack pattern is not constant, it's not stationary, and it becomes rather difficult to detect these kinds of attacks. Another issue that we need to be cautious about in terms of this aerial devices that need location and that will need location information and will be used for communication is some joint attacks. So, for example, there is these separate localization attacks and there are separate communication attacks. But the attacks formed in a joint manner can be more problematic than solely looking at one aspect of the functionalities. Now, why is it more critical in these scenarios? Is because of the wireless channel. We cannot hide the signals within a cable, and this wireless channel has two important properties. The first one is the broadcast nature, and it means that it's not confined with a specific propagation path. and because of this broadcast nature, we have multipath effects, and this causes random fluctuations. These random fluctuations cause some sort of stochastic effect on the reception, and it causes a lot of variation in the signal quality. And we also that is also problematic in terms of the detection of the presence of an attacker, because an attacker can easily hide within these distributions. So these are let's say the vulnerable points of the wireless propagation channel. An example is shown in this chart. We have an unguided communication media, and there may be multiple eavesdroppers, of course, and there may be multiple jammers within the same network. So it is prone to attacks. And of course, this is in this chart, what I'm trying to say is there is some loss as we go as the distance between transmitter and receiver increases. And in addition to that, if you combine all the effects, we have the path loss, we have some sort of large scale fading, we have some sort of small scale fading, which may change with different distributions, including Rayleigh Rice and the Kagami. And all of these effects actually make these channels vulnerable to different kinds of attacks. Of course, there are some advantages that are provided by the wireless channel due to the random nature, like extraction of some keys. However, on the overall, it forces us to think security differently. Now, if you go back to the OSI reference layer architecture, we can see that the security must be addressed at all levels, especially when it's becoming more and more problematic, or maybe more and more critical in the presence of aerial and satellite devices and mega constellations with thousands of satellites. Now, I would like to draw your attention to the cyber-physical nature of these satellites. First of all, I'll give the definition of the wireless cyber-physical system. A cyber-physical system network of physical and computational components. So it will bring together the cyber world, the physical world. That means there is, of course, some sort of sensing in the system, and there is some sort of actuator that changes the behavior in the physical world. The cyber-physical systems have a lot of applications, including a number of critical industries like energy, manufacturing, so like smart factories, healthcare, smart cities, transport. For physical systems, we have the applications and the users and the controllers, which can be distributed over the network, and each of these networking channels between them could be a wireless channel. Now, this introduces a lot of vulnerabilities in between each of the wireless channel, as I'll try to come to. But the interaction between the physical world is the main thing that we have to keep in mind. Now, it's composed of many different components, but the main components include communication, a control system, and an embedded computing module, and we have ubiquitous sensing and actuators. And the applications change from nanoscale to planetary scale, and the presence of actuators actually introduce the threat to the actual environment because of these, let's say, illegitimate data that can be transmitted to the device. Now, of course, the nature of these cyber-physical systems change according to each target application. Each of them, like medical systems, have different requirements, and drone swarms have different requirements, and their performance definitions may also change. So the service quality and the security and the quality of service should be evaluated jointly for the overall user satisfaction due to the inherent relationship between them. The security and the quality of service is not independent. That means, for example, if I would like to increase my security level by using some sort of technique to increase the energy, the battery depletion time will increase, and the quality of service will be reduced as a result of an empty battery. So there is some sort of interaction between them that needs to be considered. Now, what are these performance requirements? We have security goals and operational goals in cyber-physical systems. In the operational goals, we start with the stability due to the control nature of the system. And then we have application-specific functions that could be quality of service, quality of experience, or if it's a sensor network, it could be quality of intelligence. And of course, we have energy constraints, especially important in IoT sensor networks, that needs to be considered. In addition to those, we have, of course, resource constraints, bandwidth, and timing aspects. And additionally, we need to support heterogeneous platforms. That means various requirements can be introduced by the number of different users. And of course, when we look at the security, we have the classical confidentiality, integrity, availability requirements in the system, and the interaction between the operational goals and the security goals can sometimes be conflicting. Now we can focus on each application, and in this chart from one of our recent papers, I would like to show a couple of examples. If you look at industrial wireless sensor networks, the requirements and the performance expectations are different. Smart grid would provide a set of restrictions. Wireless by the networks would come with their own restriction, the performance criteria. And vehicle to roadside unit communications, of course, they come with their own energy restrictions and the performance capabilities, including the computational capabilities. So each of them has to be understood, and the solutions need to be tailored accordingly. Now, if we look at the common attacks and countermeasures to these systems, and we list the attacks, even the known attacks, you can see from the table that there is no solution that could be there's no technique that could address all the problems. So it needs to be. We need to look at the security from this multifaceted view, and what I'm trying to say is, in addition to the classical security approaches, wireless security mechanisms will be complementary to the current systems, and they need to be considered in a more effective manner because of the fact that the new attack types will be emerging. So what are we looking at in this distributed control system? We have the physical system, we have the sensors, we have the network, we have the actuators, and we have the control units. And each channel between each of them is a wireless channel. That means an attacker can be present there, an eavesdropping attack and or jamming and or spoofing attack can be present there. And this doesn't only look at the communication aspects, but also the location information that is also transmitted in a wireless manner can be targeted. The mere presence of the wireless channels make the system more vulnerable to these smart attacks, especially when they are coupled with the transmission signal. Now, this can help with the application of this, or the introduction of the multi-layer security, and the physical layer security becomes inevitably important, as is the first step of the security. This is a rather different concept than the classical security approaches, but with the emerging satellite networks, it is a very promising tool to be used. Now, what are some of the tools that we can use in the physical layer? Frequently used solutions include eavesdropping countermeasures, physical layer-based authentication approaches, and jamming detection. Of course, there can be spoofing detection, and the attackers are usually provide a physical presence between the transmitter and the receiver. What we can do is we can do beamforming to be able to direct the signal towards one end. We can use other transmission techniques, including full duplex communications. We can generate our own let's say jamming signal, friendly jammers with artificial noise, artificial interference techniques. And by this, we can try to avoid eavesdropping. And we can use a simultaneous transmission between these devices. In this chart, I would like to emphasize the implementation aspect. Usually, physical layer security is a technique that is perceived as mostly theoretical. However, with software-defined radio nodes, we have in our recent studies we have shown that actually we can use physical layer security techniques to avoid the reception of a signal by the eavesdropper. And in this figure, you can see the distorted constellations by the eaves in the presence of transmission of known signals from Alice and Bob to be able to distort the reception of the eavesdropper. Now, it is actually, and even without the absence of over-idealistic assumptions like the presence of the channel between Alice and Eve at Alice, it is possible to show that in practice, physical layer security techniques work. Other approaches that we can use for the physical layer security scenarios is the use of is the generation of a key, and we can generate this key based on the randomness of this wireless channel. In this case, the presence of this random effect would be served as an advantage. And of course, the key generation issue has some issues by itself. However, by using information reconciliation techniques, we can combat some of the disadvantages, and of course think about techniques to combine an embedded key with the generated key to make a compromise between the classical approaches and the physical layer-based key generation approaches. Now, if we would like to do some jamming detection, which can be an interest issue, especially in the crowded space with video constellations, and it doesn't, it doesn't have to be a jammer. It can be an unintentional interferer that we need to combat. We have done some tests using USRP devices, software-defined radio devices, and we have used some sort of different machine learning algorithms to be able to understand the anomalies in the system. For this, we have used a transmitter and the receiver and a jammer, and the jammer has generated some different patterns of jamming signal. So it doesn't have to be a classical barrage jammer, but it can be a different. We can target only the cyclic prefix. We can target only the pilot signals. So these are not easy to detect with classical averaging based techniques where the jammer's statistical behavior doesn't change in time. However, with this, we have used a convolutional neural network and RNN techniques, and we have seen that a good detection accuracy can be approached even in the presence of non-ideal conditions. However, we have observed some critical issues. First of all, the training process is extremely important. It must be accurately designed. It requires a significant amount of data, which is maybe more than necessary to be able to store like in a practical environment. And varying conditions need to be captured for high accuracy, and online algorithms with tracking capability is a must for practical usage. Now, how can we combine all of these things together? And this could be within a framework that we have proposed recently. And in this framework, we can make use of a context manager, adaptation manager, and configuration manager. What's happening here is there is a number of risks that can be a threat in this in the system, and we need to select the transmission approach based on the risks. And of course, for this scenario, it's not targeting the space, but the same kind of arguments are valid. And even more stringent from the energy management perspective. Now, for this kind of scenario, one thing was apparent to us is like in addition to like we have discussed the security goals and the operational goals. To be able to combine these goals together, we need to go to a utility metric, and the utility, of course, has to be different for every kind of application. And in this setup, we tried different examples of possible networks and try to maximize the utility both in simulations and, of course, with a simple testbed scenario. And depending on the target objective, we have seen that it is possible to improve that objective. However, definition of this objective is also not as straightforward as the definition of the minimization of bit error rate problem. There are a lot of a number of extensions to these works that we have looked on in the recent years, and we are currently trying to extend these issues with my colleagues and my students towards the use of congested mega-constellations. Now, what are we expecting for the future outlook? I would like to discuss a little bit of these issues. And for the future, we are expecting a cross-layer multi-agent applications. That means the architectural changes in the 6th generation network will be here. We will have the aerial networking elements. We will have the satellites. However, the ergodicity assumption that we keep using needs to be questioned. So that means the behaviors of the channel, behaviors of the different bands, and the behaviors of the attackers needs to be reconsidered as the problems may become a bit more tricky to tackle. And of course, we will be looking at non-contiguous frequency bands of different carrier frequencies, starting with microwave, millimeter wave, sub-terahertz, and terahertz bands, and possible extension to free space optical communications for the backhauls. Now, there will be a number of architectural challenges. If I come back to this picture, another issue that we need to consider is the capability of each node. Now we will have multi-band connections, and we will have control. Cyber-physical nature of these devices will be apparent. In addition to that, we will have computing devices, which will be able to do some of the computation in a distributed manner. So this is like the extension of the edge. And then we will also have some caching to store the data in a more effective manner in space networks, especially with long distances between the stations. And any kind of jamming, spoofing attack in this scenario will be critical. And of course, another thing that we will need to worry about is the autonomous systems. They will it will not be possible to control all these systems in a controlled manner, so that each device will have some autonomous functioning capability, and the attacks toward these towards this control architecture may be also something that we need to think about. Now, with this autonomous idea, we will see more and more of the enhanced cognitive skills on the device scale, the transmission parameters, and of course the networking aspects can be determined in an autonomous manner. That will include different bands, different data rates, different redundancy levels like error control code, varying security levels, varying energy levels. So the utility paradigm can be extended with this with the cognitive capabilities. Additionally, we can talk about the cross-layer, cross-application interaction according to the utility perspective and the perceived risk level. And this will require this can be accompanied well with the joint detection estimation problems, not only from the communication data, but also from the presence of an attacker to change the risk level. Of course, a number of issues that we need to worry about is the effective routing aspects, effective mobility management, idealized resource management, cache management, attack detection and prevention are the things that we need to worry about. Now, finally, to conclude, as wireless cyber physical systems, LEO satellite networks will have tighter operational requirements than the current wireless networks, and as apparently the networks become more critical, the security is even more critical, and we can, of course, make use of distributed machine learning approaches for a multi-layer security framework. However, the one thing is important: we need to make use of every bit of information for the security, especially in this ever critical networking environment. So I would like to thank you for your attention, and I would like to receive your questions, or if you have further questions, please send me an email at güneş.kurt@polymtl.ca. Thank you very much.
Thank you, Ganesh. It was really nice presentation, and a lot of things that were new for me. So what I would like to ask, I mean, we have a few minutes where we can do a brief discussion. Although we have some questions, but I think it will require more time, so we have a little time left in the seminar. What I can ask, that's very high level. Like now we are working, I personally work with 5G or 6G research, and we are speaking of satellite communication that might be treated as a parallel or as an alternate to it as well. I mean, not like the conventional 4G, 5G systems that we are using based on the mobile network operators. So how do you see it is changing the future like usage? We will be seeing much more people using the satellite-based communication in the future, or we will be sticking to the conventional cellular-based systems that we are using today. What's your perception?
Hi, Murdi. I will say that the terrestrial networks are here to stay for sure. However, satellites this time with the next generation satellite networks, this will be different than the Iridium. And the main issue is not only to serve the rural areas, but to serve urban areas, congested cities. The main bottleneck as of this unified view with the satellite networks is the requirement for specialized terminals for satellites, because I cannot connect to the satellite using my regular phone, and that the high path loss creates a big issue. For this, there are a couple of very interesting solutions. One of them being the targeting the deployment of a 900 square meter antenna up in the LEO band with a giant satellite. So once we can get this high path loss issue sorted out, either with giant antennas or making use of multiple receivers, like in a distributed antenna array system in the space, because of the presence of multiple satellites at all times, then it will be a reality. Then we will be able to then satellites will be able to create an alternative when I'm in the middle of the in downtown and trying to connect to the network. I'll be able to either connect to the satellites or the terrestrial network. However, currently, of course, we need to get these big satellite dishes, customized equipment to be able to connect to the networks. So once we pass this hurdle, satellites will be here to stay.
Yeah, I think I have the same opinion that one of the key challenge that we are facing is the path loss, because how to resolve this, and we are moving to smaller and smaller devices with much more functionality, and the battery power is another concern. So yeah, I think that is one of the challenge yet to be solved, and we have wonderful engineers listening to us who will definitely solve these issues in the coming years. With that, I would like to take take the opportunity to make one more announcement. Since we are doing this seminar under IEEE VTS Young Professionals, and for the IEEE VTS Young Professionals, we are setting up a body that will be working for young professionals. So if you are a PhD student, a postdoc researcher, anywhere in the world, you are welcome to reach out to me. Here is my email, and I can show you here. Yeah, so here is my email. You can reach out to me. What we are doing, we will be organizing local activities for you under the VTS Society, and dedicated to young professionals. So I think it will be something exciting. We already have two bright students, one of Ganesh student and one from King's College London, and we need a few more students to complete our board. So I think if you're listening and you are interested, feel free to contact me at email or via LinkedIn. So with that, I would like to thank you all for listening, and hopefully see you soon with another speaker. And thank you, Gunis, for your presence.
Thank you, Timer. Thank you for listening, and have a great rest of the day.
Thank you. Thank you.